In this class we will start digital modulation. In the last two classes we have discussed band pass signal representation and band pass systems representation in terms of low pass signals. That is, if we are given a band pass signal, we can represent the signal as a low pass equivalent signal, and we have seen how to derive the low pass equivalent signal of a band pass signal, and also how to get the band pass signal back from the low pass equivalent signal. Also we have seen the same thing for band pass systems. That is, for any band pass system we can construct a low pass equivalent system. Now also, if we have a band pass system and we want to give one band pass signal as input to that, and we will receive one band pass output, then we can do this whole operation in low pass low frequency. How? We can take the low pass equivalent system of the band pass system, the low pass equivalent signal of the band pass signal that we are going to give as input, then we give this low pass equivalent signal as input to the low pass equivalent system. Then we will receive one low pass signal as output. We will have one output which will be low pass. Now if we now up convert, that is take the band pass signal corresponding to that low pass signal, then we will get the output which we would have got if we gave the original band pass signal as input to the band pass system. So this is something interesting, because this way we can avoid high frequency implementation of band pass systems. We can do down conversion of the signal and then pass it through and give it as input to the low pass equivalent system, and then at the end convert the output to band pass, that is, do up conversion. So if you have a system, band pass system, you give one band pass signal as input. To get this output, instead of implementing this system, we can do down conversion to get SLT, the low pass equivalent signal of ST, pass it through the low pass equivalent system of the original system, then receive some output which will be actually the low pass equivalent signal of this output. So we can now do up conversion here to get this output. Instead of doing this way, we can do this way. And also, even if we do not implement things like this, we can at least for analysis purpose assume that the system is like this. This is one way of representing the system also. Instead of saying there is a band pass system, we can say that we can deal with the low pass equivalent signal, low pass equivalent system. You can assume that we have a low pass equivalent signal, we have a low pass equivalent system, we have a low pass output, low pass signal as output. So we can treat this, analyze this system, because the original system is equivalent to this. It is only a frequency shift. Okay. So in this class, now we will start digital modulation techniques. You must have done another basic communication course where there is you have studied analog modulation, amplitude modulation, frequency modulation, such analog modulation schemes. But here, as we said before, the digital communication will mean that even if the signal, original signal that is to be transmitted is analog, we will convert it into digital signal and then transmit in digital means. So when we are discussing in this course about communication, we will assume that the signal that is to be transmitted is digital signal. So we have a digital signal, meaning by you have samples, maybe binary or it may not be binary but digital. So but any other digital signal can also be converted into a binary signal. So we can, without loss of generality, assume that the signal we have to transmit is digital, is binary. So in this class we will start discussion on how to transmit digital signal through analog channel. Remember, the channel is still analog. Most of the channels in practice are analog channels. So, previously we discussed that there are several reasons why one should do modulation, like antenna dimension, to shift the signal in higher frequencies so that the required antenna dimension is small, then for purpose of multiplexing and such reasons. But there is another reason for modulation in digital communication. When the signal that is to be transmitted is digital and the channel through which we have to transmit is analog, obviously we have to do some conversion from digital to analog, because the ultimate transmitted signal should be continuous time analog signal. So this also requires certainly some kind of conversion. So that is also modulation. So that is another purpose of doing modulation, that is quite natural in digital communication. So, so just now we said that the channel through which we are going to transmit is continuous time. That's why we need to convert the digital signal into analog signal and then transmit. So that is one purpose. The other purpose may be, of course, again to shift the frequency also, like we said before. So there are two kinds of modulation immediately we can see. One is that the channel, maybe we don't really need to transmit in pass band. We still want to transmit the signal in low pass, through low pass channel. So the signal, transmitted signal bandwidth signal will be still low pass signal, not band pass signal. But still we need to convert the digital signal into continuous time signal. So that kind of modulation is called baseband modulation, where baseband means basically low pass. So starting from 0. So there is baseband modulation, there is passband modulation. Purpose of passband modulation is all the objectives we said before for modulation, like reducing antenna dimension, then multiplexing and all such reasons. But baseband modulation is just to convert the digital signal to analog signal and then transmit through continuous time channel. So let us first take the simplest example of a baseband modulation. You must know that in computers, for example, we transmit from one chip to another, from monitor to, from the CPU to the monitor, mouse, keyboard, all. So there is some communication between all these devices. So there is some communication going on, and this communication is essentially digital. So, but the channel, that is the cable or the connections inside the circuit board, they are all analog. They can carry continuous time signals. So how are they transmitted? They are transmitted through this simple mean, that if one is to be transmitted, if we assume that the transmitted signal is binary, the binary message is to be transmitted, then 1 is usually represented by one voltage and 0 is represented by another voltage level. So one example is 1 for plus something, say plus 5 volt, and 0 minus 5 volt. Also, of course, this is limited to time. Probably this is transmitted for transmitting 1 bit. This is transmitted for maybe few nanoseconds or few microsecond. So, and then another bit will be transmitted in another same time, this time. So this is one symbol interval. We will denote the symbol interval by t, in which one symbol will be transmitted. In this case, the symbol is a bit actually. So this is the simplest way to transmit through a cable. Now, if we do this way, then if we have, say, these bits to be transmitted 1, 0, 1, 1, 0 and so on, then what will the transmitted signal look like? It will look like this. 1 means, so say this is 0, this is t, this is 2t, this is 3t, this is 4t, this is 5t, and so on. So here in this interval we want to transmit 1. So we will transmit say plus 5 volt here. Then we want to transmit 0, so we will transmit minus 5 volt here. Then again 1, then again 1, then 0, and so on. So this is 0, this is 1, 0, 1, 1, 0 we are transmitting. So this is a typical baseband modulation. This is the simplest baseband modulation, and this whole transmission scheme can be represented in a neat analytical form, and that is, suppose this pulse, we denote this pulse as P of t. We denote this pulse as P of t. Then this is nothing but minus P of t. So we say that if we want to transmit 1, we transmit the waveform Pt, and then if we want to transmit 0, we basically transmit minus of Pt. So we have a fixed template signal, we will transmit that signal. If we want to transmit 1, we will transmit negative of that if you want to transmit 0. That is the idea. Okay. So suppose that we have now, we said that we actually don't have 1 bit to transmit, we have many bits to transmit, like we said 1, 0, 1, 1, 0. So what will be the resulting waveform we are going to transmit? Can we express this in a neat way? So for 1 bit, we know that suppose this is the 0th bit, this will be transmitted in, we call this say, we call this B0, then B1, B2, and so on. And of course, it might have started before, B minus 1, B minus 2, and so on. So this is a stream we are going to transmit. It starts from somewhere and goes on. So we don't know where it starts from, so we can say that it starts from minus infinity in general. So we are going to transmit this stream. So what is the way we have just now explained? We will rephrase it in a different way. So we say that each bit is first converted into a level, some voltage level or some real number. So B0, if it is 1, it will be transmitted, it will be mapped to plus 5 or minus 5, one of them. So 1 is mapped to plus 5, 0 is mapped to minus 5. This operation we call mapping. This conversion from the bit value to a level. And then what do we do? So after this mapping, we then, so first step is mapping. Suppose we will get some level for each bit. So for this we will get some levels. So we call that A minus 2. The level is called A. So A, the value of A is 5 for 1 and minus 5 for 0 for this example. So from here we will get A minus 1, this is A0, from here we will get A1, from here we will get A2, and so on. First we have converted the bits into levels, and then for transmitting for generating the signal, we will basically multiply. So in this 0 to t, we are going to transmit B0, then 2t, then 3t, minus t, minus 2t, etc. So we are going to transmit, construct some signal here, that is A0 times Pt we are going to put here. If this is 1, we are going to put 1 times Pt, that is it will come here. So what have we got here? This signal, if we don't put any other bits here, this signal is nothing but A0 times Pt. Then we will multiply A1 by Pt and put here. So we will shift Pt here and then multiply by A1. So what is the shift operation? Pt is shifted by T. So that waveform will have the expression P of T minus capital T. So P of we take this signal, the shift the pulse by t and then multiply by A1 and then add with this signal. So, then we will get the signal for transmission of B0 and B1. So, A0, if A1 is 0, we will have this signal if we add these two. If we add these two, we will get this transmitted signal. But we want to transmit all these signals. So, the ultimate expression for the transmitted signal is nothing but xt is equal to, for all these bits. So k equal to minus infinity to infinity, we are going to transmit bk. So, bk is the kth bit we are going to transmit. So, that will be transmitted from kt to k plus 1t in that interval. So, first we have to shift the pulse to kt, it should start from kt, multiply by ak, and we have to add all such signals for all the k's. So, we have to add ak p t minus k times t, because we are shifting the pulse by k times t. So, this is our ultimate transmitted signal, this is the expression for the transmitted signal, where AKs are obtained from these original bits to be transmitted by mapping. So, this mapping has to be decided. This is, if we have, for this example we have taken plus 5 and minus 5, but this could be anything. So, this is a typical, this is the simplest modulation we can have, a baseband modulation scheme. Now we have discussed here for this example that the PT is a rectangular pulse. We have taken PT to be a rectangular pulse, but there is no reason why this should be so. This should be so because why not have this pulse instead of taking a rectangle like this? If we have like this, what is the harm? So, this is also one possibility. So, we can say this is PT, and then how will our transmitted signal look? Again binary, we will transmit plus PT or minus PT. Let us say 1 is mapped to 1, 0 is mapped to minus 1. Instead of saying 5 minus 5, we can also map to 1 or minus 1. So, the transmitted signal for the same bits as we transmitted before will look like, say this is t, this is 2t, this is 3t, 4t, 5t. Then the transmitted signal for 1 0 1 1 0 will be 1 0 1 1 0. If you have this pulse, we will be transmitting this for transmitting 1 0 1 1 0. Now, the pulse also need not be restricted to 0 to t. It could be, for example, this kind of pulse. Then the signals will overlap and they will be added. So, it will look like they will be added. So, we want to transmit 1. So, this is t, 2t, 3t, 4t. So, when it goes to minus, it will cross through this. It will be something like this. They will have overlap. So, this part, for example, is the sum of two such waveforms like this. Sum of this is this. So the pulse can be anything. We can choose the pulse and then we can still have the same modulation scheme. So, this is a modulation scheme because we have a bit stream, the digital signal from which we are getting a transmitted, we are getting a continuous time signal which is to be transmitted. So, this is a modulation scheme. Now, instead of having these pulses, if you observe here, the rectangular pulse which we took before has the spectrum. What is the Fourier transform of the rectangular pulse? It will have the magnitude which is sinc function. So, the magnitude of the Fourier transform of the pulse is, we will have something like this shape. So this is really a passband modulation. This is not ideally if the spectrum was like this. So it would have been best. See, if we are transmitting this signal, each individual one is actually a pulse, a rectangular pulse. So Fourier transform of each one is a sink like this. But when you add them, it will also be similar to this. Magnitudes, the spectrum of the transmitted signal will be similar to this, and so it is a low pass signal. As you can see, it is concentrated to 0 and it is dying off at higher frequency. So because this is a baseband modulation, it would have been best if the spectrum of the transmitted signal was like this and then 0 afterwards, because probably you are going to transmit something else here, like multiplexing, some other signal will be transmitted here. So we don't want them to interfere with each other. But we need not necessarily use the rectangular pulse, as we said before. So we can have, instead of rectangular pulse, if we have this, this is in time domain, if we have this, for example, then its spectrum will be not be sync function, it will be something else, and it may be a better spectrum. It may be, it will have probably smaller side lobes, so that is better. So this is in baseband modulation also. There is an incentive for taking a different pulse shape, such that we can, the purpose is basically to get a better low pass transmitted signal. It should have better spectral containment. It should be contained in a smaller frequency band. It should not spill out in higher frequency. That is the idea. So it really may be useful to have different pulse shapes to transmit. Now the pulse shapes need not be this also. Suppose we don't want to transmit in this band. It is not low pass. We want to transmit in pass band. So our channel is actually, we want to transmit in this band, let us say. So it is simple, we can simply do this by, suppose this is Fc, we call this Fc minus Fc. Then we simply do this, we instead of taking, say we take the rectangular pulse shape, we can take any other pulse shape also, you can do the same thing. But let us say we take the rectangular pulse shape, this is the pulse shape we are going to take. But now we don't want to transmit this pulse as it is, because then the spectrum of the transmitted signal will be low pass. We want the spectrum to lie here. So what do? We basically shift the spectrum in two sides. So we can then multiply this with the sinusoidal signal, of frequency Fc. We will get a signal like this. So then what will happen? This signal is basically Pt times sine 2 pi Fct. Now we can also write this as Pt 1 by 2j e to the power j 2 pi Fct minus e to the power minus j 2 pi Fct. And you can see that Pt times, so 1 by 2j is a constant, Pt times this and Pt times that. So what is the Fourier transform of Pt times this? Fourier transform of Pt shifted by Fc. That is the Fourier transform of Pt times e, exponential of this. So this Fourier transform will be here, this time this Fourier transform will be here. So the resulting transmitted signal, if we take this pulse, the resulting transmitted signal will have spectrum like the sink here, shifted here. Similarly, this. So this is fine with us, because we have now constructed a signal that is passband. This is lying here where we wanted to transmit. So this is now a passband modulation. So now our pulse is not a baseband pulse. Actually what we are going transmitting, taking as pulse is this whole thing, not PT alone. PT is this pulse, but now we can say this itself is PT. This is rectangular and this P prime T. This is actually our pulse that we are going to transmit. So, the transmitted signal can still be written as xt summation k equal to minus infinity to infinity ak times P prime T minus kt. Now, the pulse is P prime, that is all, and P prime is not a rectangular simple rectangle, but a sinusoidal signal multiplied by that rectangle. So, it is a modulated pulse. It is a modulated pulse, and but this expression remains same for the transmitted signal, whether it is a passband modulation or baseband modulation. Only the pulse will change. The pulse itself for baseband modulation will be low pass. So, it will be a rectangle or like this, but for passband modulation it will be a passband signal, band pass signal. That is the difference between passband modulation and baseband modulation for this kind of modulation at least. Now, okay. So, we have seen that for baseband the pulse for baseband and passband modulations only the pulse shape will be different, and the otherwise the expression is same and the way you do the modulation is also same. So, we will take now a particular example. Now, for so far we have seen only binary modulation, all these are binary modulation, and this kind of modulation is called pulse amplitude modulation, because what we are basically doing is that depending on the bit that is to be transmitted, we have first taken a pulse, and depending on the bit that is to be transmitted, we multiply the pulse by something and then transmit. For example, we can multiply by +5 and -5 for 1 and 0, or 1 and -1 for 1 and 0, and then transmit. So, that is what we are doing before. Now, it is not necessary that it has to be +5 -5 +1 -1 like this. It can be some constant like 2 times PT for 1, 3 times PT for 0. Similarly, if you have you can have different other ways also, we will see later. So, for binary modulation we have seen so far that we have been actually changing the amplitude of the pulse by multiplying something and then transmitting. So, the amplitude of the pulse is transmitted depending on the bit that is to be transmitted. If it is 1, the amplitude is something, if it is 0, amplitude is something, we are doing it negative. So, why just binary? We can in fact combine two bits together, 3 bits together and transmit more bits in one symbol interval. That can also be done. For example, let us say we want to transmit 2 bits at a time in one symbol interval. So, you have 0, t, 2t, 3t and so on, and we want to transmit 0 0 here, 0 1 here, say 1 1 here, and again 0 1 here, and so on. So, we want to transmit 2 bits at a time. So, that means if we want to do the same thing as before, we need 4 values of amplitude. We cannot just take +5 -5 like that, because that is 2 levels. Using 2 levels we can transmit only a binary signal. To transmit 2 bits at a time we need 4 levels, because there are 4 possible values for the 2 bits. It can be 0 0, it can be 0 1, it can be 1 0, or it can be 1 1. So, we need 4 levels. So, let us say that for this example, let us say for 0 0, so this is the mapping we are doing. Map it to some level, some amplitude. So, this is 1 volt, let us say 1, 0 1 goes to 2, 1 0 goes to 3, 1 1 goes to 4. Then modulation, in the modulation we will take multiply by PT. So this will be PT, this will be 2 PT, this will be 3 PT, this will be 4 PT. This is the way we will do the modulation. So if we take PT to be again rectangle, because that is the simplest case, easy to draw. If we take that, then what will be the transmitted pulse? 0, T, 2T, 3T, 4T. So here we want to transmit 0, 0. So the level is 1. So 1 times PT. So we will transmit 1 here. Then 0, 1. We want to transmit 2. So 2 times PT. Then we want to transmit 1, 1. 1, 1 is mapped to 4. So 4 times PT. We want to transmit 4 times PT here. And then we want to transmit 0, 1. So 0, 1 is again 2. So and so on. So for this mapping and for this rectangular pulse, this will be the transmitted signal for this bit stream, So here this modulation scheme, now we have seen that we are transmitting 2 bits at a time. What is the advantage? The advantage is that obviously we are transmitting more bits per symbol. So the data rate we are transmitting is more now. Previously we were transmitting 1 bit per symbol, now we are transmitting 2 bits per symbol. So now what is the compromise we are making here? Can we really stack more and more bits in one symbol and lose nothing? That is certainly, that must be impossible, otherwise there will not be any problem in communication, right? So there are different ways of looking at it. Suppose that we have some battery power restriction. Our mobile, for example, if the battery lasts for 1 hour, then the mobile is of no use, because we have to charge every 1 hour. We have to recharge the mobile every 1 hour. So there may be power restriction. How much power you can transmit, that there is some restriction on that. So then the pulse amplitude that you are going to send, there must be some restriction on the power. So you should not transmit too much average power. Okay. So now what will that mean? If you now want to put more and more levels in that restricted interval, then you have to have, so if you have different levels here and all the levels have to be now congested in the same interval, then we need to have this difference between these levels as smaller than what we have now. Suppose you want to put 8 levels in the same interval, then we will have very small difference between the levels, and maybe when it is corrupted by noise we cannot distinguish between the levels. So that will be the problem. We will analyze this case more later, but for time being we will remember that there is some restriction in practice in putting more and more bits in one symbol interval. So this is 4 PAM we have considered, and in general this same technique can be used for transmitting multiple number of bits, any number of bits. This is for, we have 2 bits, so the modulation scheme is 4 PAM. So in general we can have M PAM, where M is 2 power B. When we want to transmit B bits, that will mean 2 power B levels. And so if we now have so many levels and we multiply by that level to the pulse amplitude and then transmit, then that is the M PAM. So far we have seen how binary PAM is done, we have seen how passband modulation is done and how baseband modulation is done. What is the difference? The type of the transmitted signal is basically same, the only difference is in the pulse shape. The pulse for the passband modulation will have a baseband spectrum, low pass spectrum, whereas the pulse for passband modulation will have band pass spectrum. So that is the difference. And we have seen that instead of transmitting only 1 bit per symbol interval, we can in general transmit any number of bits per symbol interval, though there will be other things we need to compromise for that. For example, if we don't want to compromise on probability of error, then we have to increase the battery power, the transmitted power to transmit more bits, because then we don't want to compromise on probability of error. That means that the difference between the levels should not be reduced very much. If they are reduced, then when they are corrupted by noise, when the signal is corrupted by noise, we will not be able to distinguish the different levels. So difference between the consecutive levels should be kept high to have sufficient minimum low enough probability of error. So then what is the way of increasing number of steps? Only way is to increase the range of values, range of levels. So that will mean transmitting more power through the channel, and that means again battery power if it is operated by battery or whatever. So we have seen in general that we can transmit any number of bits per symbol using pulse amplitude modulation, but we have to compromise on something. We have to transmit either more power or we have to compromise on probability of error. So now what is the way to demodulate this signal? We have, let us say, using a rectangular pulse, we have transmitted some bits. We still consider binary modulation because this is the simplest. Suppose we have transmitted this 1 0 1 1. Then how do we demodulate at the receiver? Suppose the channel is just AWGN, that means only noise is added, white Gaussian noise is added. Then this signal will be corrupted by noise and it will look like something like this. And then at the receiver we want to estimate these bits we have transmitted from this received signal. Now one obvious way that comes to our mind is that we just sample at one point here, this sample value, and see whether it is positive or negative, right? So that is one way of doing it, but that is not the best way, because this is very the noise will create a lot of problem with this kind of detection scheme, demodulation scheme, because the noise is additive white Gaussian noise. So it can be from the value of the noise can be minus infinity to infinity, any value. So at this particular point the value may be really negative. So though the signal really looks very nice, here it is positive everywhere, but it may be negative at a very small range. So if you amplify this part, the signal may look like this, but it is fairly clear that 1 is transmitted in this interval. But if you just happen to sample at this moment, then we are in trouble, because then we have detected 0 instead of 1, because this value is negative and we will think at the receiver that probably the transmitter transmitted 0. But we can see that the other parts of the pulse is fairly nice. So we should also take into account all these values instead of sampling only at one place. So one way to do it is just add all the sample values. So most of the values will be positive, So we will detect better. But most of the add more samples means what? We are still leaving out these samples. So we should in fact take all the values, take into account all the values and then decide. So one way to do it is just take the integral of this signal in this interval 0 to t xt, the transmitted signal, received signal, this will be yt. So then what will happen is that because the noise is white Gaussian noise with mean 0, the parts where this is negative will be fairly small. So this will still have positive area if one was transmitted most of the times. So we can take this value, this is the area of this curve. So this part will contribute negative, these parts will contribute towards the positive. So this value will be hopefully positive. So this is a better way of demodulating the signal, and we will analyze this in a different way and see that see how to implement such a system. So what do we want to do? We want to do integration of the signal. We want to integrate the signal for detecting, first of all, from xt. Just like at the modulator, at the transmitter we had first mapper and then modulator, at the demodulator we will try to do exactly the reverse sequence. From xt we will try to extract ak, all for different k's, for first k equal to 0, then k equal to 1, k equal to 2, so on, and then from ak we will try to estimate bk, the kth bit or kth bits. It may be many bits in the same symbol, so then we will try to estimate all the bits in that symbol. So in this we are saying this operation we will do kt to k plus 1 t xt dt. This is what we will do. So this is kt, this is k plus 1 t. We transmitted bk in this interval. So we will integrate xt in this interval, and then that will be the estimate of the value ak. So this is the estimate of ak. This is the integration of xt from kt to k plus 1 t. Now this also can be expressed as, remember that this is our pt is, this is our pt we have taken for this case, this is the pt. So this can be written as this can be written as this, because what is the product of xt and pt? Pt minus kt. Pt minus kt is basically the shifted version of the pulse. It is the pulse shifted by kt. So now Pt minus kt is basically, so this is somewhere 0 here, and this is kt, and this is k plus 1 t. So P t minus kt is this signal, and then we are multiplying that with xt. So what we will have is this part of xt. Other parts will be multiplied by 0. So those values will be 0. So this is same as this. It is same as integrating in this interval, integrating xt in this interval, because only this product will be non-zero only in this interval, and in that interval the value will be equal to xt. Okay. So this we can write as this can be written as, we can verify that it can be written as star xt. What is the formula for this? This is the convolution of xt and this at, we want to evaluate this at k plus 1 t. So, what is the convolution here? Suppose this is, we call this is yt equal to t minus capital T minus small t. So, we want to evaluate it at k plus 1 t. So, in place of t we will put this. So, the convolution formula is xt, then k plus 1 t minus t. So, if this is yt, then the convolution is y k plus 1 t minus t xt dt. So, yt is this. So, in place of t we will put this. So, it is basically t minus in place of small t we will put this whole thing. So, k plus 1 t plus t dt. So, this is equal to this. We can see that 1 t cancels. So, then t minus k times t, we have this. So, this is equal to this, but then this is equal to this. To see this, suppose consider that this signal is yt, then convolution of yt with xt is at this time is y of this time minus t then xt dt. Now, in place of t put this whole thing here, then we will evaluate this function at this point, we get this. So, what we have seen here is that this what we wanted to have, actually this turns out to be same as p capital T minus small t convolution xt evaluated at this point. So, what we have here is that a filter, because convolution means filtering. So, what we want to do is pass xt through a filter with impulse response this is xt. When you pass it through this, we get this convolution. Then we want to have the value at this point. So, we sample it at different, every t seconds we sample. So, for m equal to k plus 1, at k plus 1 sample will be the value of ak. So, here we will get discrete values. The values will be ak. First we will get a0, a1 and so on. So, here we will have a0, a1 and so on. So, the k plus 1th number, these will be estimates of course, k plus 1th number will be the ak hat. So, we have seen here that to do demodulation of the PAM signal, where we have used the pulse, rectangular pulse, we have seen that this is one way to do it, and this is equivalent to doing convolution with xt. This convolution of this p, this is again the pulse of course, it is same as pt in this case, but later we will see the significance of writing it this way. So, we have seen that this can be implemented in terms of a filter this way, first filtering xt and then sampling at different points. Those will give us AT, and from this of course we can do demapping. If A1 is positive, we say it was 1, and if it is negative we say it was 0. So, in this class we have seen binary modulations first. We have seen that there are different ways of taking the pulse shape we can have rectangular, that is the simplest, but we can have also different other pulse shapes to shape the spectrum appropriately. And then we have seen that instead of transmitting binary signal by using PAM, you can transmit b number of bits at a time in one symbol interval, and that will be 2 power b PAM, that is called MPAM, where m equal to 2 power b. And we have seen just now how to demodulate such a signal. Instead of sampling at one time and then deciding on that sample, we have seen that we will do better by integrating the signal in that interval to decide what was transmitted in that interval. And later, finally, we have seen that can also be done in terms of first passing that can also be done by passing the signal through a filter with impulse response, rectangular impulse response, and then sampling the output at multiples of t. So in the next class we will see more on this demodulation. We will generalize this situation for different pulse shape. What should we do for rectangular? This is the case. What is the best way to do for other pulse shapes? We will do that in the next class, and that will be masked filtering. So in the next class we will start with masked filtering and go ahead. Thank you.